All right, so now we're going to take a look at some specific examples involving density. As a quick reminder, density is simply equal to the ratio of a substance's matter in it to the space that it occupies, which is its volume. So if we were able to measure the mass and the volume, then we can simply substitute it into this equation and solve for the density. Okay? So sometimes this is abbreviated as D equals M over V. And as an equation written this way, we can rearrange this. So this can be rearranged algebraically to solve for any of the three uh, things that we see in here. So obviously this is relative to D right now. We can rearrange this, solve it for M, or solve it for V if we needed to, depending on what is it that we're trying to find. So this can be rearranged as any of the variables. Okay, so let's take a look at examples involving maybe a couple of examples involving the use of density in calculation. So let's say a sample of lead has a mass of 0.5, 0.7 grams, and then we're told that the density of lead is 11.3 grams cubic centimeter. And we need to figure out what is the volume of this lead. Okay, so if you have any questions, as you've seen previously, you want to organize the information. So what are we given here? In this case, we're given the mass M, 25.7 grams. We're given the density as 11.3 grams per cubic centimeter. And what we need to find is the volume. That is our unknown. So what are we going to use? Well, we need to use a relationship that connects D, M, and V. Obviously, it's going to be our density equation. We need to rearrange this now to solve the volume, right, which is in the denominator over here. So there are a couple of ways. There's usually more than one way to approach this, depending on what works best in your brain. You will choose one way, which if you have a quick way to do this is something called cross multiplication. So for example, if I put the D over 1, and anything over 1 is the same thing, I can cross multiply this way, so I end up with D times V is equal to cross multiply that way, M times 1 is M. Okay, dV is equal to M. And then to isolate V on the left side, I can divide this side by D. D cancels. This is an equation, so whatever I do to one side, I need to do to the other side as well. So I end up with the volume being equal to the mass divided by the density. And I know what the mass is, I know what the density is, I can substitute these into an equation to solve for V. So V then is equal to the mass, 25.7 grams, and that's divided by 11.3, density 11.3 grams per cubic centimeter. Okay, stick that in your calculator. You want to follow your sig fig rule. So we got 3 sig figs in the numerator, 3 in the denominator. So we should have 3 sig figs in the answer. So 25.7 divided by 11.3. Okay, and that gives 2.743, blah, 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 blah. And then the units here, grams cancel away. We end up with 1 over 1 over cubic centimeter, which is cubic centimeter. We're going to round this to 3 sig figs, so that's right here. So this then becomes 2.27 cubic centimeters, or we could say 2.27 milliliters of the cubic centimeter is the same as a milliliter. All right, so the density equation itself fairly simple in terms of the three variables that are there. We need to be able to manipulate this, rearrange it to solve for any of the other any of the variables that we see in there. Now, another way you can approach this problem is if we're given these few things. Let's do this in a different way. It's a different approach to this, which ends up being the same thing that you're doing in the first approach anyway, but I'm going to show you this way because this really has a lot to do with the dimensional analysis that we talked about earlier on. Okay, so if I have my mass here as 25.7 grams, and then my density is 11.3 grams per cubic centimeter, right? This density is actually a conversion factor. That tells me I can write this as 11.3 grams per cubic centimeter, or I can flip it. Cubic centimeter on top, every 11.3 grams at the bottom. Now remember, grams per cubic centimeter means grams for every 1 cubic centimeter, right? So these are my two conversion factors that I have. From the density relationship, I have the mass that I start with. Right, I want to end up with eventually volume, whichever unit of cubic centimeters on top. So this then dictates that if I were to use one of these two conversion factors that I get from density, I'm going to probably select this one because it's got the unit that I want in the right place, right? It's got the cubic centimeters. You can get conversion factors, like we talked about them, getting them from equalities in the metric system or between the metric system, the prefixes between the metric system and a different system. You can get them from things like density as well. So you can get them from all over the place. So I'm going to select this conversion factor because it's got the unit that I want where it needs to be. And then I also need to incorporate the mass in there, right? So if I set this up, okay, I'm going to take my conversion factor first. So let's put that 1 cubic centimeter for every 11.3 grams. I select this one because the cubic centimeters in the numerator. And then I have my mass here, 25.7 grams. And put that over 1. And guess what? Grams cancel. Right? So just in terms of the units, without even thinking about the density equation, I'm just looking at the value for the density and the units involved, the units of mass that's given, and I'm just applying the same principles of dimensional analysis to cancel out units and end up with a unit of volume that I want. And guess what this ends up being? Ends up being dividing the 25.7 by the 11.3, which is exactly what we did up here. Right? So this is just another way to get to the same endpoint, and you'll see this a lot when you do calculations. There's not just one way to solve it, right? You can do it multiple different ways. So you end up with cubic centimeter as the only unit remaining. 25.7 divided by 11.3 gives us the same value, 127 centimeters. Okay, so just a different approach in terms of how you set it up, but what you end up doing is the same thing if you were to rearrange that density. So whatever way it works for you, do it that way. Okay, don't turn your whole world upside down. If you're able to solve this one way and then you learn something else and it just confuses you, just stick with the way that that you're comfortable doing. Okay, so that's a quick sort of recap of what density is, how we can use the density equation, not just to solve for density, but also to rearrange it to solve for any other thing. All right, I also want to talk about a couple of things, a couple of terms. Just like we saw, we talked about mass and weight that technically mean different things, but we sometimes use them interchangeably. We talked about that before. Let's talk about two other terms that are often used interchangeably, but actually mean different things. And those two terms are accuracy and precision. Okay, so again, sometimes depending on what you're relating to somebody else, we may use one term when we actually mean the other term. So let's define them first, and then we'll see the differences again. So accuracy is a measure of how close you are to the true, or sometimes that's referred to as the accepted value. Okay, that's a measure of accuracy, and we often can quantify that by calculating something known as percent error. In a measurement or whatever it is in an experiment that you're doing, the percent error is going to give us an idea of how accurate you are. How close are you to the value that you're supposed to get, the true value or the accepted value for something? Precision, on the other hand, is a measure of the repeatability of a measurement. Okay, and this then is going to be influenced by the instrument, the measuring instrument that's used. And this is where the whole idea of sig figs is going to come in. Sig figs, etc. Okay, so precision, a measure of the repeatability of an instrument, or repeatability of a measurement, dictated by the instrument use. Accuracy, how close you are to the true or the accepted value for that. So I'll give you an analogy here. Let's say that we have a dartboard. And we're throwing some darts to it. Obviously, you throw, maybe not obviously, but you want to aim for the bullseye. That's our goal. Right here in the center is what we're aiming for. Okay, and let's say you throw some darts at this, and first time you throw it, you find that, oh, the first dart ends up here, the second one ends up there, third one ends up there, fourth one ends up there, and the fifth one ends up there. Okay, so obviously, you are not throwing the darts close to the target. So you are not close to the true target or the true value. So that means then, according to this is not accurate. Okay, the true thing you want to get to is the middle, right? The bullseye. However, these 5 darts that you threw are fairly close to each other, right? So we can say that these are precise because every time you throw the dart, they end up at roughly the same place, right? So maybe your aiming is off, but it's consistently off. So it's a precise, meaning it's precise meaning that you're repeating the same thing over and over again, but you're not close to the true value. Okay, let's say that you throw a different set of darts and we end up with something that looks like this. So one dart goes here, another one goes there, one goes down here, one goes there, another one goes here. So here, the green ones, you can see that they're all spread out, so they're not repeatable. These are not precise. Okay, and then they're also not close to the bullseye, not close to the true value. They're also not accurate either. Okay, and that's kind of like the worst case scenario. Not even close to each other, not even close to the true value. Now let's say now I throw a third set of darts and I see that the darts end up here. There's 1, there's 2, there's 3, 4, and 5. Okay, so these are clustered together here in the middle. So that means it's repeatable. That means that it is precise. And then they're also fairly close to the true value. So then they're also accurate. Okay. So that's what you want to aim for whenever you make, not just in this analogy with the darts, but when you make measurements, you want to to be careful with your measurements. You want to use the correct instrument so that your precision is the best that it can be. And you also want to be very careful with how you actually how you make the measurements, follow the proper procedure, proper rules, so that you are as accurate or as close to the true value as you can possibly be, because we will make some calculations to actually determine the accuracy by calculating something known as the percent error. Okay, so let's take a look at an example of one of these. So let's say we'll go back to the what do we use here? The lead. Okay, so let's say in an experiment, student determines the density lead in, let's say, 3 trials. So they did the same experiment 3 times, and if they reported the density in the 3 trials as follows. So they got 11.5 grams per mil, trial 1. Trial 2, they got 11.4 grams per mil. Then trial 3, they got 11.6. Okay, so we can do a couple things with this. First thing you want to do is we can calculate the average density of lead, and then calculate the percent error. So one thing we can do before we do those calculations is just by looking at the values here, without even knowing what it should be, we can see that these are fairly close to each other. Close to each other. So that tells us then, generally, we can say the measurements were precise, right? So they're repeatable, we're getting roughly the same value every time. So let's calculate the average first of all. For the average, it's simply adding together all of the values and then dividing by the number of values that we've had. So we take 11.5 and add that to 11.4, add it to 11.6. Here's it. All the values added together. We divided by a total of 3 trials that we did. We divide it by 3. Let's see, 11.5 plus 11.4 plus 11.6. Divide that by 3. Imagine you're getting right smack dab in the middle, 11.5. The middle. That's the average values, average density, for the density of lead. So that's the first thing. The next thing we can do is calculate the percent, and the percent error is calculated as follows. So we're going to take the calculated value. We're going to subtract the true value. We're going to divide that by the true value. A couple terms that you may see being used interchangeably. The calculated value is often referred to as the experimental. And the true value is often referred to as the theoretical. Or sometimes the true, but we already said true. Or theoretical value. Okay, so we just calculated the average. So this here, right, we just calculated. So obviously this is the calculated value of the experimental. So what's the true or the theoretical value for the density of lead? Well, that's something then that we're going to have to look at. Okay, so this we can look up in a textbook or online, or in this case, we were told what it was. We go back. In this question here, the density of lead is 11.3 grams per mil. So we know what that is just by 11.3 grams per milliliter. So all we need to do then is to substitute those values in here. And whatever we get, we're going to multiply it by 100 to convert it into a percentage. Okay, that's the formula for percent error. I'm going to substitute those values. Calculated was 11.5. I'm going to subtract 11.3. That's the true value. We're going to divide it by the true value, 11.3. Whatever we get, we're going to multiply it by 100. Substitute that into my calculator. So 11.5 minus 11.3. Divide that by 11.3. I'm going to times that by 100. Okay, so that gives me 1.8%. Okay, and obviously now the percent error is an indication of how close you are to the true value. Okay, so that's an indication of the accuracy of your experiment. In this case, we have a really small percent error, and that's good. Okay, that's what you want when you do your experiments. That's an indication of your technique and your measurements and all that stuff. So this means then that we're fairly accurate. Okay, so this error or this calculation or derivations of it are things that you're going to be using down the road when you do your analysis and everything else. Calculating the percent error is going to be important. So knowing what the calculated value is, that's what you get from doing your experiment. The true value is what something should be, right? You can look that up, or maybe it's given to you. The difference there, you divide it by the true value, and then you times by 100. So sometimes, you end up with a percent error that's positive. That just means that you're more than, or your calculated value was greater than what the true value is. If you get a negative percent error, that just means that your value was lower than what it should have been. Okay, so sometimes people just take the absolute value of the percent error and then you explain what it actually means. If you don't take the absolute value and you just look at the signs that you get, then if a negative percent error arises, that just means that what you got was lower than what it was supposed to be. And you get practice doing this when we do our first lab exercise as well.